For generations, the story of human evolution was taught as a clean, linear progression. It was a comfortable narrative, often depicted in the famous March of Progress illustration, where a crouching ape gradually stands taller, sheds its hair, and strides confidently into the future as a modern human. In this orderly timeline, Australopithecus afarensis, best known through the famous fossil Lucy, served as the perfect protagonist. She was the bridge between the primitive and the modern, the definitive moment when our ancestors descended from the trees and claimed the African savannah. However, the fossil record is rarely as tidy as our textbooks suggest. As paleontologists have returned to the scorching badlands of East Africa, sifting through millions of years of sediment, they have uncovered evidence that shatters this simplistic view. The discovery of mysterious footprints that do not match Lucy's anatomy, along with fossils of strange neighbors living right alongside her, has revealed a much more chaotic reality. We now know that bipedalism was not a singular stroke of evolutionary genius, but a messy, dangerous series of experiments. Lucy was not the lonely grandmother of humanity marching toward the future. She was merely one character in a crowded, competitive drama played out on the stage of the Pliocene epoch. The story of this scientific revolution begins with a moment of serendipity that would define paleontology for the late 20th century. In 1974, the Ethiopian landscape of Hadar was a place of blistering heat and barren dust, a geological window into the distant past. It was here that Donald Johanson and Tom Gray were conducting a survey, working with what was then a fragmentary and frustrating fossil record. Prior to this expedition, the understanding of human origins was pieced together from isolated scraps. A single tooth here, a jaw fragment there, a piece of skull found miles away. The scientific community was trying to assemble a jigsaw puzzle with 90% of the pieces missing. That changed on a November morning when Johansen spotted a small arm bone weathering out of the slope. Unlike the isolated scraps found previously, this bone led to another, and then another. Within hours, the team realized they had stumbled upon something unprecedented: a 40% complete skeleton of a hominin that lived 3.2 million years ago. As the team celebrated in their camp that evening, blasting the Beatles song "Lucy in the Sky with Diamonds on a Loop," they christened the skeleton Lucy. Lucy was a revelation because she presented an anatomical contradiction that fascinated researchers. Her pelvis was not the elongated, narrow structure of a chimpanzee. Instead, it was bowl-shaped and flared, possessing the specific architecture required to support the internal organs of a creature standing upright. The angle of her thigh bone relative to her knee confirmed that she walked on two legs. To the scientific community of the 1970s, she was the missing link made manifest. She offered tangible proof that our ancestors stood up long before their brains grew large, as her cranial capacity was roughly 400 cubic centimeters, barely larger than that of a modern chimp. For decades, Lucy stood unchallenged as the benchmark of early human ancestors. She was the icon of the Australopithecus afarensis species, the singular vessel through which the ape lineage began its transition toward humanity. But hidden within her bones were secrets that would eventually complicate this pristine narrative. While the world celebrated Lucy as the first walker, biomechanical experts began to notice details that did not quite fit the narrative of a fully terrestrial creature. The contradiction lay in the upper body. If Lucy was a dedicated walker who had abandoned the trees, her arms told a different story. Her humerus, the upper arm bone, was heavily built with robust muscle attachment sites that hinted at immense upper body strength. Her radius and ulna were elongated, creating an arm-to-leg ratio that was far closer to modern apes than to humans. The most damning evidence, however, was found in her hands. The finger bones were curved, not straight. This curvature is a specific adaptation for hooking onto horizontal branches, allowing for a powerful grip when hoisting body weight against gravity. This sparked a fierce debate known as the functional versus vestigial argument. One camp of scientists argued that these tree-climbing features were merely evolutionary baggage, leftovers from a primate past that were slowly fading away but served no active purpose. They viewed Lucy as a committed groundwalker who retained these primitive traits simply because evolution had not yet selected against them. However, the opposing camp pointed to the sheer robustness of these features. Natural selection is a ruthless editor. It typically eliminates traits that are energetically expensive to maintain unless they provide a survival advantage. Maintaining dense bones and thick muscles for climbing requires significant metabolic energy. The persistence of these features suggested they were not useless leftovers, but vital tools for survival. Lucy, it seemed, was living a double life. She was a creature of the ground who had not yet let go of the sky. To understand how Lucy moved, scientists needed more than just bones. They needed to see her in action. In 1976, 2 years after Lucy's discovery, Mary Leakey's team at Letoli in Tanzania uncovered one of the most spectacular finds in the history of paleoanthropology. A nearby volcano, Savannah, had erupted 3.6 million years ago, blanketing the savannah in a layer of fine, cement-like ash. Rain had fallen shortly after, turning the ash into a pliable mud that captured the movements of the entire ecosystem. Solidifying like concrete, the ash preserved a trail of footprints extending nearly 90 feet. These tracks were made by 3 distinct hominin individuals walking together. The preservation was so exquisite that it captured the mechanics of a moment that occurred millions of years ago. The analysis of the Letoli footprints provided the hard evidence needed to confirm the efficiency of australopithecus bipedalism. The tracks revealed a deep heel strike, showing that these individuals landed forcefully on their heels before rolling their weight forward along the outside of the foot and pushing off with the toes. This heel strike toe-off pattern is the hallmark of modern human walking. Furthermore, the footprints showed a distinct longitudinal arch, a shock-absorbing mechanism that apes lack. Most critically, the big toe was adducted, meaning it lay in line with the other toes rather than sticking out to the side like a thumb. In apes, the big toe is divergent and opposable, used for grasping branches. The Letoli prints showed a foot that had been remodeled for the ground, sacrificing grasping ability for the leverage needed to walk long distances. These prints confirmed that 3.6 million years ago, hominins were not shuffling awkwardly. They were striding with a confident, energy-efficient gait that rivaled our own. The discovery of such modern feet at Letoli seemed to contradict the primitive arms of Lucy. If their feet were perfected for walking, why did they retain the heavy, curved arms of a climber? The answer lay not in anatomy alone, but in the terrifying reality of the Pliocene environment. East Africa at this time was a mosaic of environments featuring open grasslands, woodlands, and riverine forests. It was a land of plenty, but also a land of monsters. The predators of this epoch were nightmares of biological engineering. Saber-toothed cats like Dinophilis and Meganterion prowled the brush, equipped with serrated fangs capable of delivering fatal wounds to the neck. Giant hyenas with bone-crushing jaws hunted in packs, while the waterways concealed crocodiles far larger than those of today. For a hominin standing barely 4 feet tall, possessing no natural weapons like claws or large canines, the ground was a theater of constant danger. In this context, The climbing adaptations of Australopithecus afarensis were not evolutionary leftovers. They were an insurance policy. The ability to scramble up a tree in seconds was the difference between life and death. This led to the dual adaptation hypothesis. Lucy and her kin were ecological generalists. They exploited the expanding grasslands for food during the day, walking efficiently to cover vast distances between resource patches. But when night fell, or when a predator emerged from the tall grass, they retreated to the canopy. This compromise allowed them to thrive in two worlds, accessing resources that neither a pure ground dweller nor a pure tree dweller could reach. As researchers accepted this dual lifestyle, the complexity of these early hominins continued to deepen. For decades, it was assumed that technology, specifically the creation and use of stone tools, was the defining characteristic of the genus Homo, appearing much later in the timeline. Small-brained australopithecines like Lucy were thought to be incapable of such cognitive feats. That assumption was challenged in 2010 by a discovery at Dakika, Ethiopia. Researchers found fossilized animal bones dating back 3.4 million years, the same era as Lucy. These were not ordinary fossils. They bore linear gouges and scratches. Under microscopic analysis, the marks displayed V-shaped cross-sections, a signature left by sharp stone flakes. The placement of these marks was even more telling. They were clustered around the joints, where tendons must be severed to remove a limb, and along the shafts of long bones, consistent with smashing bone to extract the nutrient-rich marrow inside. If this interpretation was correct, it meant that Australopithecus afarensis was using stone tools to process meat nearly 1 million years before the first formal stone tools appear in the archaeological record. This sparked a firestorm of controversy. Skeptics argued that the marks could have been caused by trampling cattle or, more plausibly, by the teeth of crocodiles, which can leave similar striations. However, if the tool hypothesis holds true, it suggests that Lucy's species possessed a level of cognitive planning and behavioral sophistication previously denied to them. It paints a picture of a creature that was not just a passive part of the food chain, but an active manipulator of its environment. Using sharp stones to access high-calorie resources that fueled their survival. The final blow to the linear March of Progress theory came in 2015, with a discovery that proved Lucy was not the only game in town. In the Woranso Mila area of Ethiopia, just 30 miles from where Lucy was found, researchers unearthed fossils that belonged to a contemporary but distinct species. They named it Australopithecus diaremida. This new species lived between 3.3 and 3.5 million years ago, overlapping perfectly with Australopithecus afarensis. But anatomically, they were different. Australopithecus diaremida had a more robust jaw and smaller teeth, with thicker enamel, suggesting a diet that required heavier chewing forces. The true shock, however, came from the foot bones discovered nearby, at a site called Bertel. While Lucy's species had the modern arched foot seen at Laetoli, the Bertel foot told a completely different story. It possessed an opposable big toe, similar to that of an ape, or the much older hominin Ardipithecus. This divergent toe meant that the owner of this foot could grip branches with its feet, making it a superior climber to Lucy. However, this climbing advantage came at a steep cost. On the ground, this creature would have lacked the efficient toe-off mechanism. It would have walked with a flatter, less efficient gait, likely pushing off from the side of the foot or the second toe. This discovery was revolutionary. It meant that at the exact same time in human history, there were at least 2 different experiments in bipedalism running simultaneously in the same valley. One species, Lucy's, prioritized efficient walking while keeping some climbing ability. The other, the owner of the Bertel foot, prioritized arboreal agility while managing a clumsier form of walking. The existence of these two species side by side raises the question of how they avoided direct competition. The answer likely lies in niche partitioning, a concept where different species utilize different parts of the environment to minimize conflict. Isotopic analysis of tooth enamel has provided the key to this puzzle. By measuring the ratios of carbon isotopes, scientists can determine whether a creature ate C3 plants, which include fruits, leaves, and shrubs found in forests, or C4 plants, such as the tropical grasses and sedges of the savannah. The data revealed that Australopithecus diaremida had a diet heavily skewed toward C3 resources. They were forest specialists, sticking to the woodlands and relying on their grasping feet to access fruit and shelter in the canopy. In contrast, Australopithecus afarensis showed a mixed signature of C3 and C4 isotopes. Lucy was the ultimate opportunist, eating forest foods when available, but also venturing out to consume grasses, seeds, and perhaps the meat of animals grazing on the savannah. This dietary flexibility may explain why Lucy's lineage seems to have persisted longer and arguably led to future success, while the forest-bound lineages eventually faded as the African climate continued to dry and the woodlands shrank. The accumulation of this evidence, the climbing arms, the stone tool marks, the divergent footprints, and the neighboring species, forces us to abandon the old linear model of human evolution. We can no longer view the path to humanity as a straight road where one species improves upon the last. Instead, the Pliocene epoch was an evolutionary laboratory. Nature was running multiple experiments simultaneously, testing different combinations of traits to see what worked best in a changing world. There were many ways to be a biped. There were walkers who could climb, climbers who could walk, and perhaps tool users who still slept in trees. Lucy's dark secret was never really a secret. It was the complexity of life itself. The realization that she shared her world with other bipeds, that she was a mosaic of ape and human traits, and that her era was one of diverse experimentation rather than singular progression, makes the story of our origins far more profound. We are not the inevitable result of a predetermined plan, but the survivors of a rigorous process of elimination descended from a lineage that happened to have the right mix of adaptability when the climate turned against the forests. The footprint of humanity is not a single track, but a tangled path of trial, error, and survival.